Okay, good evening, ladies and gentlemen. This is Professor David J. De Los Reyes. The date for tonight will be April 24, 2025, and the time is 23:44 military time. It's for 16 minutes before 12 o'clock. Okay, my topic for this evening will be a continuation of my long video format topic, DC circuit. It's been a long time since I don't have a long video format on my DC circuit because I'm busy with my shorts videos on the so-called troubleshooting of refrigerators. So for tonight, I will be continuing the DC circuit long video format topic. So for those of you who are taking up electrical engineering, this is for you guys. Okay, let's proceed. The subject matter for tonight will be DC circuit lesson number 31. I am now, or we are now on lesson number 31. We are almost done. So for tonight, it will be DC circuit lesson number 31, and the title of the topic, this is Norton's Theorem problem. Lesson number 31 is a continuation of lesson number 30 because my plan is this. I solved a problem on lesson number 30 and I will be presenting a marathon solution on that problem. Marathon solution meaning I will be presenting different concepts of solution, and the concentration will be, the answer will be the same on all the concepts. So we are now on the marathon solution number 2, and that marathon solution number 2 is actually Norton's theorem problem. Norton's theorem. We will be solving the same problem. Okay, the first time around the solution was Thevenin's. So for tonight, I will be presenting the Norton solution, and supposed to be the answer will be the same. Okay, let's try to bring out the problem. This problem here is the same as problem lesson number 30. The circuit is the same. The problem is just asking what will be the current passing here. And that will be designated by capital letter I with the subscript 8 ohm. And that will be the one we are to solve for tonight. Okay. The first solution, according to lesson number 30, the current is actually 1.551 amperes. That is using the Thevenin's solution. And that was actually lesson number 30. Okay. So for tonight, we will be presenting the solution, Norton solution, and supposed to be what will come out will still be 1.551 amperes. Okay, I will try to check my camera. Oh, it's fine. Okay, let's try to bring out the solution. Solution, okay? A very, what you call this, systematic approach on how to solve a problem. Step number 1, under Norton's theorem. Under Norton's theorem, okay, we will disconnect the 8 ohm, then short the terminals, and solve capital letter I with the subscript SC, meaning the short circuit current. So, step number 1, we will remove this 8 ohm here, and we will be shorting the terminal. Okay, that's step number 1. Then after that, if we try to place an ammeter here, ammeter, it's an electrical instrument that measures direct current, right? We will be solving for the current passing here, and the designation of that one will be capital letter I with the subscript SC. That is step number 1. So we remove the 8 ohm load, we short the terminals, and across the terminals, first terminal here and this one, the one where the 8 ohm emanates, we will place an ammeter, okay? and we will compute for the short circuit current. In actual, there is no problem because if we try to remove the 8 ohm, we will just place our ammeter here and we could determine the short circuit current by using the ammeter. But theoretically speaking, if we are on the board as an engineer, how could we compute for the short circuit current? Okay, it is something like this. We redraw the circuit like what I said. We remove the 8 ohm, then we place our ammeter here, and we must have to compute for capital letter I with the subscript is C. Sorry for that one. Capital letter I with the subscript is C, meaning the short circuit current. We will try to compute this one using our knowledge of the concept of electrical engineering. Okay? There is an annotation here. When the 8 ohm is short circuited, no current will pass through the 8 ohm and the 6 ohm. I will try to remove the ammeter. I will just short this one. If this is short circuited and this 18 volts will try to bring out the current, okay, that current will not pass through the 4 ohm and 8 ohms because there is a shorting wire over here. Okay, there is a shorting wire. If this is short circuited, the current emanating from the 18 volts will not pass through the 4 ohm and 8 ohms. So it seems this is gone, and so with this. Or the part of the circuit that will be just existing is just that one. If this one is shorted after the removal of the 8 ohm, this 4 ohm and 6 ohm have no effect on the circuit. Okay, so actually we could compute for the short circuit current now. If we try to visualize the circuit, it is just an 18 volt source connected in series with the 2 ohm load. So by using the equation voltage equal to IR, okay, we could compute for the current. It will be voltage over R. And for this resulting circuit, after the shorting of the terminals, the voltage will be 18, right? And the resistance will just be simply 2 ohms, this over 2. So what will come out for the short circuit current is 2 amperes. So this will be with the value 9 amperes. This one here. It's a big current. Because if we short this one, like what I said, this has no effect and this has no effect because the current will pass through a circuit with the least resistance. And since this 4 ohm and 6 ohm is actually greater than the resistance of the shorting wire, we assume that the resistance of the shorting wire is 0. So if the current enters here, instead of going to the 4 ohm, it will just go directly to the shorting wire. So the 4 ohm and the 6 ohm has no effect. Okay? So step number 1, we have computed already the short circuit current. That's 9 amperes. Again, I will check my camera. It's 9 amperes. Step number 2, find the open circuit resistance across the terminals after shorting the 18 volt source. So step number 2 will be something like this. We'll try to short out the voltage source. We short it out. So it seems this is gone. Okay. Then we replace this meter here by, instead of an ammeter, it should be an ohmmeter. So we will be computing for R in here across this. But we must have to short out the 18 volt source. So if we try to short out the 18 volt source, the configuration will be this one here. This will be the resulting configuration. This is actually where the 18 volt source is located. Okay, we short out the 18 volt source, so the corresponding figure will be something like this. This is just the ohmmeter. Okay, so with respect to these two terminals here, this 4 ohm and 6 ohm are actually in series, so the single equivalent, sorry for this one, the single equivalent will be 10 ohms. The single equivalent of this, it's 10 ohms. Okay, so this is 10 ohms, this is 2 ohms, and with respect to this two terminal, this 10 ohm and 2 ohm are actually in parallel. So if we now try to compute for capital letter R with the subscript N, meaning the Norton's open circuit voltage, capital letter R with the subscript N, this N here refers to Norton's. Rn now will be two resistances in parallel. It will be just simply the product all over the sum. So this will be 10 times 2 all over 10 plus 2. This is 10 and this 2. So if we try to take the single equivalent with respect to this terminal here, it will be the product all over the sum. And with what will come out for the open circuit resistance will be 1.67 ohms. That's step number 2. What will be the last step? For Norton's theorem equivalent, step number 3 will be draw the Norton's equivalent circuit. We now know the short circuit current. We now know the so-called open circuit resistance. So if we try to follow the concept of Norton's according to the Norton's theorem, the short circuit current, if we try to do the circuit, will be in parallel with the open circuit resistance. Okay? And this is actually the terminal where the 8 ohm actually emanates, this one. Okay? So this portion here is actually the Norton's equivalent. According to the Norton's, if we try to perform step number 1 and number 2, step number 1 is this one. We have computed for the short circuit current. Step number 2, we have computed for the open circuit resistance or the Norton's open circuit resistance, 1.67, and these should be in parallel. If we try to refer to Norton's, these should be in parallel. Then we will try to reconnect the 8 ohm load. We try to reconnect the 8 ohm load, the original resistance in which the current we are computing. So if we try to figure out the circuit now, the circuit is just a parallel circuit. Okay? If the total current coming here is short circuit, I capital letter I with the subscript EC, considering this junction, the current entering this 1.67 will be I with the subscript EC minus the current passing through the 8 ohm load, because this is I sub 8 ohms. Right? Current passing here will be the total current I subscript EC minus I sub 8 ohms. And since this part of the circuit are actually in parallel, the voltage across this should be equal to the voltage across this. So the voltage across this part of the circuit will be I short circuit minus I sub 8 ohm, the current passing here, times 1.67. And this should be equal to the voltage across this should be I sub 8 ohm times the 8 ohm resistance. So this should be I sub 8 ohm times the 8 ohm resistance. Okay? And if we try to simplify this one, this is now just pure algebra. 1 I short circuit times 1.67 is this one. I sub 8 ohm times 1.67, this is now negative. And this should be equal to the right hand side. I times I sub 8 ohms. So if we try to transpose this to the right, okay, we put this one to be equal, this negative, right? We put that to the right, so they will now be similar terms. Okay, the only unknown now will be I sub 8 ohm. So I sub 8 ohm will be the I sub 8 ohm. Okay, this is 1.67 plus 8, and that is actually 9.67. Okay, so if we try to compute for this one, it should be the product 1.67 times the short circuit current, which is 9, all over the sum of 8 plus 1, which is 9.67. And 1.67 times 9 is actually 15. And 15 over 9.67, what will come out will be 1.551 amperes. And this current here is actually the current passing through the 8 ohm load, the 8 ohm. Okay? And this with the value 18 volts. This is 18 volts. Okay? So the current passing through this 8 ohm here, according to our computation, it's 1.551 ampere. That is by using Norton's theorem. And from the previous lesson number 30, in which the solution was Thevenin's, the current is still 1.551 amperes. So for tonight, we have presented the second concept of solution. And supposed to be, the current that will come out will be the same as for the first solution. Okay, that's it, guys. So we are solving one problem and we are presenting a marathon solution. Marathon solution meaning the different concepts of solution. So the first solution, Thevenin's, the current is 1.551 amperes. And the second marathon solution is actually the Norton's theorem solution. Okay, and the current is still 1.551 amperes. Okay, for those colleague of mine who are in the Philippines, if you could follow my lecture, just follow it. Okay, my topic is Norton's equivalent for tonight. The last time around, I was discussing short videos on refrigeration and air conditioning, and you are following it. Thanks for following me. Okay, so for tonight, the answer will be 1.551 amperes. So for those of you who would like to follow my channel is at youtube.com/@ProfDavidJ. Okay, the contents of my channel actually comprises of long video format topics on mathematics and electrical engineering. So this is actually my 10th subject, complete syllabus. Okay, and I am finishing this one, and the other one is actually the analytic geometry. And I have uploaded already a complete syllabus on 10 subjects on differential calculus, integral, differential equation, advanced math, DC circuit, algebra, trigonometry, and the other one, plus the other one, analytic geometry. It's 10 subjects already. So for those of you who would like to take up engineering, my channel is a good reference if you would like to try to finish up your engineering without any hardship on the subject matter of mathematics. I'm not telling you that I was the one who will be the best for this subject matter, but at least if you would like to watch my channel, you will learn something from it. And for those who are watching around the world, okay, this is for you guys. Whether you are from India, from Pakistan, or wherever, this is for you guys. Anyway, there is a translation already on the English language because according to our alma mater, Google, they will be translating the English. Since I'm speaking English, this could be translated to other subjects throughout the world. Okay, I think that is more than good enough for tonight. This is Professor David J. Good morning already here in Los Angeles. Good morning.